Alright, so this is going to be problem number 5 in your book. The problem where you have a loose crate on the floor of a railroad flat car. So we got our flat car here. Let's change to pen. So we got the flat car, crate. Say the flat car is moving this way at a speed in the book of 48 kilometers per hour. And so let's do a free body diagram. I'm going to kind of emulate it like you'll often see on the AP exam. Really, they usually just give you a dot, which represents this object. And so let's do the free body diagram. You've got the forces coming from it. You got Fg. You got F normal, which should equal Fg if it's not accelerating up or down. And if the crate is moving this way, then and slowing down, then friction is going to try to stop it going that way. Force of friction. Like that. Alright? They don't give us the mass of the block, they give us the coefficient of static friction, mu s, here, equals 0.25. And again, static means not moving, so it's the coefficient of friction between these two when they're not moving relative to each other. So it asks what is the shortest distance possible that the train can stop? In other words, what is the largest acceleration possible in order to stop without having the crate slide? Which means, in order to have the crate not overcome this force of friction. As we discussed in the intro video, you know this force of friction adapts, it changes, it evolves depending on the force being applied to it in the opposite direction, right? In this case, though, this is the net force. There is only friction acting on it. It essentially has an inertia, and as the train slows down, the floor decelerates one way, which will exert a friction force on the block in the opposite way, and it will cause that thing to slow down. So let's set up our net force equation. So this is the only force. Again, these two balance out, cancel each other out. So F net equals MA, and this is the sum of all the forces acting in the direction of motion, which in this case is either going to be left or right. And so the only force horizontally is force of friction. Alright? So the force of friction, we know, is, let's just rewrite the net force, mu, in this case static, times the normal force. Right? And here's our normal force right here. And because the block is not accelerating up or down, the normal force equals the weight. Alright, so what is the weight? The weight is mg. We typically don't actually want to write this over here on the free body diagram, so we'll just substitute it here. So the normal force is just the weight, and the weight is m times g. And something nice happens. So we essentially got ma equals mu s mg. So let's rewrite that without all the middle gobbledygook. Equals mu s mg. Bam, bam. A equals mu s g. Alright? So that's our acceleration. We know mu, and we know g. And so A essentially equals on mu is 0.25 times 9.8. A is 2.45. I'm actually going to stick this over here so I don't lose it. A equals 2.45 meters per second squared. Okay, well, now that we know the A, then how do we figure out the distance? Oh my god, we still need kinematics. Kinematics, what? Still need it, so let's do it. Which one? We need distance. We have acceleration. Check. We have initial velocity. Check. We know the final velocity, the train's stopping. Check. 3 givens, that's all we need. And we're looking for, excuse me, delta x. So that equation you should remember or look up on your data table or your equation table. We have v final squared equals v initial squared plus 2 plus 2 2a delta x. V final is 0, so we got delta x equals v initial squared over 2a. Look at the units for a, m, meters, seconds. Look at the units for velocity. I hate when they do that. That's what you're thinking, right? I know you're thinking it. So let's convert before you get too angry and bash a computer screen. 1 hour every 3,600 seconds. Cancels out the hours. 1,000 meters for every 1 kilometer. Cancels out the kilometers. What does that equal? Bring over our good old trusty calculator. 48 times 1,000 divided by 3,600 equals 13.3. Alright, so 13.3, excuse me, delta x equals 13.3 repeating squared over 2 times acceleration is up here, 2.4, 5, erase, whoa, 2 times 2.45, can't win. Anyway, so delta x equals, so square this puppy, divided by 2, divided by 2.45, that's a little 4 there, not a 9, equals 36.3 meters. That's our answer. If we slow down in a distance shorter than this, this thing is going to slide. If we slow down in a distance longer than this, then the force of static friction is going to adapt, and it's going to be less and less and less. The longer this distance is, the less this is, until we approach an infinitely long distance where the force of friction is infinitely short. How's that for a little philosophical gobbledygook? Bye.